Record. There is no recording. We can't hear anything. Okay, we can't hear anything today. It's I can just well stop this presentation now. We not have this. Hi, and where is hi?
Video panel there.
Finally, okay. Okay, yes. Okay, forget everything you saw. And now we Okay, great. Okay, thanks for coming to my talk.
I'm trying to keep an eye on the chat.
It's great, and also I'm audible then. That's great. So, Christmas theme talk. Here's my beautiful Christmas tree. The talk is about this Christmas tree. What is this Christmas tree? Well, of course, it's a median network. So how do we see it's a median network? Well, first you have to admire the nice colors and the nice red Christmas balls and the nice little arrow, a golden arrow at the top. And then we turn it around. Whoa. And this is a median network. And if you want to see it in a more standard notation, this is what it is. This is the talk about today. So this is a median network, or it's an instance of a comparator network. And you should see this as a function that takes in a bunch of inputs on this side, 25 inputs. And then the inputs travel through this network, and out comes one other output at the end, over there. And that's the median of these 25 inputs. And how do we compute it? Well, the network consists of these things called comparators. They connect one wire to another wire, so they connect two wires. And what does the comparator do? Two inputs come into the comparator. They either just travel through it, or they switch depending on which one is bigger. So the comparator makes everything large go to the top and everything small go to the bottom. So let's say that. Doesn't matter because these work in both ways, but let's say all the big things go to the top and the small things go to the bottom. So we can think of a comparator as a two-sorter. It takes in two inputs and it sorts them. You can also think of a comparator as a minimum and a maximum vibrating to one component. Depending on what you do, if you're in hardware and software, these views may make a difference. But I'm just going to say comparator. Right. And this network is a network of 94 comparators, which is the best in the world. So that's what this talk is about. As far as I know, it's the best in the world.
Did you patent it?
Sorry?
Did you patent it?
Oh. No, I mean, my computer is right now thinking it may find one that's a little bit smaller than this one. I'm not convinced that this is the best I can do, but the best I can do for now. Right, okay, and finally, this is called a layer. It's a bunch of comparators that are grouped together because they're independent. So you can do them all in parallel, and that's nice. So this network has 94 comparators, but it has 15 layers. So it's 15 parallel steps. All of these things you can do in one step because they don't depend on each other. So that's also a nice property, please. Okay, so why am I interested in medians? So why should anyone be interested in medians is one question you may have. And the other one is, why would you be interested in these networks? Let me tell you. So, why medians? Well, the basic way medians are used a lot is in image denoising. So here's an example of somebody who asked a question on Stack Overflow a couple of years ago saying, I implemented image denoising in Python and it doesn't really work. And so he posted an image of himself. And so this is what the image is. So here's an image with noise. It's so-called salt and pepper noise. So some pixels are black and some pixels are white, and they shouldn't be, as you can see. And so you can denoise the image using median filtering. And how that works is that you take a little grid, for example, a 3x3 grid of pixels everywhere. And maybe the middle one is 0 and it shouldn't be. So you replace the middle of the grid like that with the median of those values. So the median of these 9 values is 21, so you replace them with 21. If you do that everywhere, then you get a nice denoised image. So that's nice. But why should you care about image denoising? Well, maybe you don't care about image processing, but maybe you care about the LIDAR in your car. That there's sensor data coming in and it has noise in it. For example, when it's raining or snowing or other things. So I've spent the last week reading papers about these kind of things. And one way to denoise these things is using median filters. There's other ways of doing it, but one way of doing median filtering. You can denoise astronomical data. Maybe you're taking pictures of the sky, several pictures over the world of the same part of the sky, or maybe you're taking several pictures different nights, and you want to sort of combine them all and see what actually is happening. Then you can do image denoising also using medians. In machine learning, of course, machine learning has applications of medians, something called median smoothing. So if you get lots of data and maybe some of it is no changes to my device. No. Okay. So and you have lots of data. The data comes maybe from public sources, and maybe somebody is trying to contaminate your data by doing very specific things. Maybe they're trying to break into, or maybe they want to make your neural network do things that you don't want it to do. Well, then you can smooth the data by taking medians of things, so there's a tiny fraction that somebody tries to doctor with the data. Well, that will disappear when you do medians. Another thing that happens in machine learning is maybe you have something that does sorting or computes medians, and you want to differentiate this because that's what you want to do when you do machine learning. Well, if you do normal sorting or median algorithms, there's like discrete steps in them, and that you can't differentiate that. But these networks, they're just data flow networks with min and max in them, so they are easier to differentiate. This is a cool new thing that came a few years ago. Anyway, so what are the size of the medians that we need to do? Well, typically when you do image denoising, you may have a 3x3 grid, so that's 9 values you want to compute the median. Or if you want to be a little bit more expensive, you can have a 5x5 grid. It's important that these are odd numbers. Why? Because the median is well defined for odd number of inputs. Because by the way, what is the median? I guess everybody knows. You sort it and you pick the middle value. If you don't have an odd number of elements in your array, you don't have a middle value. But I'll get back to that later. Maybe astronomical data denoising also use a 5x5 window. When you do LIDAR data, maybe you get 3D data. So there's 3 dimensions. So maybe you want to have a 3x3x3 cube that you want to denoise. Or maybe one of your dimensions is time, and the other is you have 2 dimensions. So then you also have a 3x3 cube. In median smoothing, you want to have any values between 3 over 32 or something like that. And so these are nice smallish numbers. Let's remember that. Okay, so these are all the applications that I found about medians. I don't work on any of these applications myself. I just like to play with networks. Okay, so why networks? Why would you be interested in computing a median using networks? Of course, we all know how to compute medians, right? Well, I mean, if you want to do this on an FPGA or actually make dedicated hardware for that, these kind of networks are basically the only way that you can sort or compute medians. You have to do it like that. That's how you make you have to have some kind of data flow network to do this. So if you're in this world, then that's the only way you can do it. But you say, well, I'm on my CPU. I know how to make median algorithms. Well, maybe, but the number of inputs is sort of small, and 32 is smallish. And so you get a lot of leverage out of using these networks. So maybe you think about quick select, which is a linear algorithm, or maybe you think about radix median, that does bit filling if you like that. It's also linear, but these are much, much slower than using a network for smaller input sizes. And why is that the case? Well, the LU, any modern LU has min-max as a primitive operator in it, so you don't have to branch. So there's no branching. You don't have to say, if this value is larger than that one, I do this, otherwise it's that. If you don't have branching, you don't have branch mispredictions. So your CPU is doing all the pipeline you can do, right? But also you get instruction level parallelism. You can do a SIMD if you want to compute multiple medians at the same time. All of this is very smooth and nice, and the CPUs behave really, really well for that. So that's really great. And so it blows any of these algorithms out of the water for small number of inputs. And maybe you say, well, I'm not on my CPU, I'm on my GPU. Well, you have similar advantages on the GPU. For example, GPU AOs also have min and max. So it just becomes a data flow network. There's no branching. No branching is great because all these little processes that are in the same block, they all do the same thing because they have no branching. So they all compute the same function. That's really good. And finally, you have these parallel layers. You can exploit that on the GPU by doing all of the things at the same time. So all of these are good things. that make these networks interesting, even if you're in software. Questions? Great. Okay, I will spend some time looking at the history of media networks. So here's some history. So I found online, I looked in people's offices when they were there. I hoped that they would have this book, but I couldn't find a physical copy of this book. There's a book called Graphics Gems, and there's 5 volumes that came out during the 90s. This one is the volume 1, published in 1990. And it's full of people who write little pieces of code. Hey, this is how you can do this graphics-related function. And Paeth, Alan Paeth, who's he has written very many chapters in these books. He writes how to compute the median of 9 inputs using this piece of pseudo C code. And so he defines a macro S2AB, that's a comparator, and it's written as if you compute B minus A, if that's smaller than 0, then you swap A and B by doing this plus and minus trick. Very, very, very cool. Maybe because the CPU he was using did not have a min or a max operator built in. And then he defined a bunch of macros, just call S2, and finally he makes this C code that has 20 comparators in total to compute the median of 9 inputs. So that's the earliest piece of code I could find where somebody actually spent time on trying to optimize number of comparators. But then in 1996, I found this magazine. It's a quarterly journal for people who like FPGAs, I use FPGAs. And they can send in things, hey, this is what I did in FPGA. And there, in that one, there's a page where somebody makes a median network of size 9. And it has, his name is John Smith. Very hard to search for John Smith. It's 90 comparators, and they turned out to be the optimal. It's the best you can do, 90 comparators to compute the median of 9 inputs. And you can see here what he's doing. He has a 3 sorter here, so there's 3 inputs, and you can sort 3 inputs using 3 comparators, and he sorts those, and then combines it, and finally you compute the median there. So that's an idea that will turn up again. Anyway, also in this book, Graphics Gems, people refer to it. Alan Paeth, he wrote this chapter about median of 9 inputs, but he says in the chapter, I also made one for 25 inputs. It's too big to fit in the margin or something, so I put it in the appendix. The appendix is not in the book. But in the introduction it says, this book comes with an appendix full of source code. It's all public domain. You can find it where you find your public domain source code in 1990. I don't know where people found their public domain. Maybe they called into these BBSs or something like that. I couldn't find this source code anywhere. But then, did some sleuthing, and finally I found an FTP server in Switzerland where there is a zip file that contains all of the source code in these appendix. So
not in Russia.
Not in Russia, no. So here's that source code. And it's 99 comparators to compute the median of 25. So this is a piece of C code, and this is a macro. The macro is not even defined here because you can define it yourself depending on what you want. And that's 99 comparators. So that's the best we can do in 1990 already. Right, okay, so that's what people use to compute the median of 25. And then, here's a graphical drawing of that. What's the first thing you think about? Not very pretty. It doesn't look like a Christmas tree. so I don't like that. But you look at this, and so what he does, and he doesn't describe how he comes up with this network, but you can look at it and see he is dividing up the inputs in groups of 3 and using 3 sorters. That's what a 3 sorter looks like. It takes in 3 inputs and 3 outputs, and it sorts them. And he has a bunch of those, but wait, 25 is not divisible by 3, but 27 is. So there's 9 3 sorters, but he's cut away the bottom wire, the bottom wire and the top wire, so those are gone. And that's why this is only a crippled 3 sorter over there, and also a crippled 3 sorter over there. And he does that 3 times. So he sorts the groups, and then he sorts the maximum of those again, and then he sorts them again. So it's like he divides the 27 inputs into a cube, a 3 times 3 by 3 cube, and he sorts each of those rows, and then each of those columns, and then each of those layers with 3 sorters. So he has, let's see, 9 plus 9 plus 9, 3 sorters. That is, how many 3 sorters is that? 27. Yes, that's how he starts with, and then you end up here, and then he somehow fixes this to finally compute the median. That's the That's the strategy he uses, I think. And Mary thinks so too. Because, oh, by the way, there's all kinds of free sorters hidden in this network. There's one there. So there's many free sorters. And there's one at the end as well. So Mary saw this. And she thinks, how can I describe this ugly network? There's no structure in it whatsoever. So she writes a beautiful paper. It's called Finding Regularity, Describing and Analyzing Circuits that are not quite regular. And it's written in 2003. It's a beautiful paper. It shows how to use nice recursive functional descriptions. I'm not going to show it to them because my talk is not about this. To describe networks like that. But she found that when she tried to describe it, your network was smaller than the one that was there. So Mary does this for 25 inputs, and she comes up with this network. It's a little bit more beautiful. It looks more like a Christmas tree. And again, the strategy is the same. You take 27 inputs, take all the three sorter stuff. There is one three sorter. Mary uses this type of three sorter. That's also a three sorter, but it looks a bit different. And it cuts the wire. But towards the end, she does different things. And so also this is full of free sorters. That's a free sorter there. Do you see it? Oh, there it is. And so everything on the right is all about free sorters that are there. Anyway, and so in the paper, you have a 98 comparator network, but then you also write a paper that you have a version of it's even smaller, 96 comparators. Okay, then you would say in 2003, we know how to compute the median of 25 inputs. We just use Mary's 96 comparator network, and that's the end of the story. So, 2025, I keep reading people who compute median of 25 using networks. These are the NVIDIA docs. They say how to do it on their GPUs. And they give this comparator network, and I was looking at it, wow, that's a very small network. Look at these red ones, you can even cut away, they say, so it's only the blue ones. I was worried, maybe they already solved this problem. But then, no. You have to also add 5 instances of this network before. What is this network? It's a 5 sorter. So they take the 25 inputs, divide it into 5 groups of 5. Each of them you have to sort, and then you use this other network. And so you get in total 119 comparators. And, okay, I don't know. I'm not an GPU expert, so maybe this is faster. But I don't think so. I think 119 comparators is going to be slower and takes more energy than doing it with 96 comparators. So today, 2025, people still don't know how to do it, although there are papers from 1990 that say how to do it better than this, and from 2003. So I'm just adding one more paper to that list because my network can do it a little bit better than Mary.
Do they have fewer layers or something?
No, I mean, look, they don't even try to make layers here because look, there's like a lot of emptiness here. They could have done things in parallel, but they don't. Or maybe this picture doesn't. But that's, when they describe it, it's just that. I think so. But again, I'm not a GPU expert. NVIDIA people presumably are.
But could there be some physical limitation, like the distance of the components from each other or something like that?
For 25 inputs, I don't think so. But yeah, but again, I don't know.
Yeah.
It would be a fun master's project to actually check what was the best way of doing it. Anyway, so how do we find small networks like this? So one thing is to use your brain. Mary did that very much, and Paeth probably also did that. So I use my brain also, but my brain is not as big as Mary's when it comes to these kind of networks. I have to say I'm limited by my brain power, so I have a subsolver that is my friend. And also I like beautiful networks. I want networks that look like Christmas trees. I'll tell you why. It's not only pleasing to the brain, but also pleasing to the subsolver. And finally, there's one thing that we need to talk about. That's the 0-1 principle. It's a beautiful principle. Knuth describes it in his book about sorting networks. And it's surprising when you hear it the first time. But the 0-1 principle is, if you have a sorting network, or a media network, any network of comparators, it is correct if and only if it's correct for only zeros and ones. So they can sort any kind of data, floating point numbers or integers or any kind of data you can think of. But if it's correct for just booleans, it will be correct for any type. And that's because you can't do any control decisions on whether or not one is larger or not. You can only flip or not flip. That's the only thing you can do. So that's really nice, right? Because if we want to check the correctness or reading about anything about these sort of networks, we just use booleans. And that's a really good fit with our subsolver because it can only reason about Boolean. So that's good. Okay, so how do we find that network like this? We have an odd number of inputs. We have one output that needs to be the median. How do we find it? Here we have strategy. It's not controversial. Everybody who searches for these networks has this strategy. You have something that you call the prefix. You fix it. You guess. These are the comparators that we have to start with. And it's very small. And the reason why it's small, I'll tell you later. And then the rest we have to search for. So I have a subsolver that can search for that. Okay, so I have to make a reasonable guess here. Well, here's a reasonable guess. For 11 inputs, we have to compare these inputs somehow. We may just well compare some of them that are independent. Does it matter where we do it? Not really. Why doesn't that matter? Because if this network is correct, any permutation of the inputs will still make it correct, right? Because any permutation of the input, the median doesn't change. So where we exactly input these comparators doesn't matter. As long as they're independent. And this is only the first layer, I'm guessing, so they have to be independent. So it does not matter where we put them. So I just put them here to make it look nicely symmetrical, like a Christmas tree. Okay, so here, here I have to skip this wire. This wire can, or one wire has to be skipped. I decide to skip the middle. Okay, so once we have made that guess, we can have the subsolver go. And then what we have to do, we have to guess the number of layers that will follow this thing. And it's not so hard to guess. We sort of have tables of what we think are the best networks. And so you just follow those tables and maybe you guess one more layer than what you actually need. And so, okay, so then you guess the number of layers. And for each layer, we just add one variable. It represents a symbolic choice between all possible comparators you can have here. So we pick one variable for every possible comparator. That's 11, choose 2 comparators. And then we add a constraint saying for every y, you can only have one comparator. At most one comparator. And moreover, we need to, and of course there's a constraint saying the total number of comparators must be less than m for some chosen number m. For target, this is the number of comparators we want. And then we have a symbolic layer like that. You need to know how to apply it when you have a vector of inputs coming into a layer, how to apply the layer to something and so it can compute its own output. So it'll have the sorting logic in it. So if there's a comparator between these wires, then I sort them like that. And so you can take a little bit with your subsolver and have very nice representation of that. And then, okay, so now you have this green stuff that lives in the subsolver. Now you have to tell it what it should do with the inputs. So we go to this fixed prefix that we have, and we enumerate every possible outputs that can come out of the fixed prefix. So that's what's on these wires. So if we did that here, if our prefix was empty, it would just be 2 to the power of the number of inputs, and that's very often a large number. So if we have a prefix, that helps us to get down this number. So we enumerate all possible vectors that can be on this one, 0 and 1 vectors, and we filter out the ones that are not already correct. So some of these vectors will already be correct, meaning that we'll have the median of this wire already, and everything that's bigger there and everything that's smaller here. So those inputs outputs that we don't have to think about because the layers won't destroy that median, it will just stay there. But any output that we have that's not already correct, we feed that through the layers, and what comes out, we say that must be the median. And so for 11, for this problem, I think it's about 450 such inputs. So that's a nice number. It's not very large. Okay, and now the subsolver is ready, and so we let it do its thing. It's thinking. Bam. Then it says, this is the network that I want. And this is not the optimal size. I'll tell you why this is not optimal size later. But the first thing I think when I see this, what do you think when you see this? It's a beautiful, ugly, no Christmas tree. This is also a pretty hard subproblem, even though it's only 11 inputs. It's pretty big, and there's lots of choices you can make. And there's several reasons for that. So one is the prefix was so very small, I didn't really get any information from it. And why is it so small? Because I have an odd number of inputs. I don't know how to decompose odd number of inputs. I don't know how to make a nice symmetrical problem out of an odd number of inputs. So that's in the way this prefix is so very small. The only reasonable guess I can do is that I need to have the one layer of comparators here, and that's it. So I want this to be larger. But I also want to reduce the search in this problem here. So I want symmetry. I would like these networks, if you flip them over, it still computes the median. That's what I want. So I want to search for symmetrical networks, not for these ugly, weird, non-Christmas tree looking networks. But it's impossible to have a symmetric network when you have comparators, because two comparators, one comparator compares two wires. And if you have enough number of wires, in every layer there must be at least one wire that's not touched. So what wire does it need to be if for the network to be symmetric? Well, the only way you can have a symmetric network if you never touch the middle wire. Then you can flip it over and everything's nice. But if you don't touch the middle wire, you can't compute the median, right? So it's impossible to have to say to the source over your network must be symmetric if you have an odd number of inputs. But odd number of inputs is what we need for median. So this is hard. And then one morning, I was awake very early, and I realized, why don't I just do median for an even number of inputs? And then, yeah, fix it up somehow. So, number of inputs will be even, then everything is fixed. So, let's do median for 10 inputs. So suppose we had a way of finding a median for 10 inputs. What does it do? Well, it comes in with its inputs here, and it doesn't compute one median, it computes the two median in the middle. And my print function for networks, it automatically puts an arrow on the output if it's the correct one in the sorted. So this means these outputs are actually the ones that you would have computed if you had sorted the whole thing. So that's the two middle median ones, and they're also sorted. And look at this nice network, it's nice and symmetrical. Very beautiful. But it has 10 inputs. I want to have a median network for 11 inputs. So what do? How do we add the extra wire? Any ideas?
Three sorter.
A three sorter? Yes. So okay, by the way, the sub problem is nice for this because it's symmetric. I'll show you why it's symmetric later on top. The extra input we just put in the middle, and then what we do? Almost a three sorter. We don't have to put a three sorter because it's already sorted. These two are already sorted, so we just have to merge the unsorted wire with the two sorted ones. And that only costs two comparators. So here it is. This is the 11 sorting network. I just made a little bit more space to the middle wire. We're not touching it, not touching it, not touching it, but at the end, we have two comparators, and now that's the median. My print function says so, so it's true.
But
So, yeah.
they're already. I guess, okay.
You only need to know the middle wire and the 10 inputs to get the final wire of the 11 input.
Right. I thought there might be a shortcut to only do one, but you need to compare two.
Yeah, you need to compare to that. Right, so that's the idea. That's the first idea I had. So now we're in even land, and I love even land so much because everything is symmetrical. Okay, so it just costs two more characters. Okay, so what happens when you have an even number of inputs in this story? But a fixed prefix, it cannot be larger because I can do more guessing. So, so for 10 inputs, this is what I guess. I'll tell you how the guessing works later on. But now I have more comparators here. The more comparators I have in the prefix, the less number of inputs I can have as the output of the prefix. So the smaller the subprogram becomes. But it becomes even smaller than that. Because now for each layer I only need half the number of variables. Because each layer is symmetrical, so I don't have to say I either have a comparator there or there. If I have one there, I must have one there as well. So every comparator I have, its mirror image must also exist. So I only need half the number of variables per layer. That's good. That significantly cuts down the subsolver. But also, I'm going to enumerate the outputs that come out of the prefix, but I only need half of those outputs. Why? Because if one output is there, its mirror and flipping the zeros to ones will have the same effect on the layer as if I hadn't reversed it. So for every output, there's a mirror and flipping bits that will have the same effect on the other layers because it's a symmetric network. So I only have to have half the constraints. So I have my number of variables and I have my number of constraints. That's really good. That's better than half constant effect on the subsolver because of course the subsolver is exponential in the worst case. So that's really good. So now the problem becomes tractable. And I send them through and I add the correctness, and of course now I have to add the correctness of two outputs instead of one. So that's a little bit more complicated, but not very much. Okay, so how do I guess the fixed prefix? So okay, let me tell you what I mean. It's a reasonable guess, right? So I can't prove to you that what I do is the correct thing, but it's shown to be good. And here's for 16 inputs how I guess what the fixed prefix is. So I have 16 inputs. Well, I may just as well compare each pair of input with comparators independently, right? I mean, I have to do that, and it's nice to have even number of inputs, so all of the wires are involved. And now what can I do? Well, I have all the maximums. I have no clue how they're related to each other, and I have all the minimums. I have no clue how they're related to each other. But I never want to mix up minimums and maximums against, because I know the minimums they're somehow in the smaller part and the maximums are in the bigger part. But maybe I should compare all the maximums. So recursively, I take the 8 maximums and guess a nice prefix for those, and I also take the 8 minimums and get a nice prefix for those. And I can do those in parallel because they're completely independent. So that's what this looks like. So again, I'm guessing what I do with all the maximums and the minimums, and I may just well compare them in any order, doesn't matter. Okay, but I'm not done. I have 4 groups. I have maximum maximums, maximum minimums, minimum maximums, and minimum minimums. Again, I can guess the right prefix for them, and it can be all done in parallel, like that. And finally, now I have 8 groups of 2. I have no clue how they're related. I may just well compare them, like that. Okay, so that's what happens when you have 16 inputs, a power of 2. I keep dividing by 2, so every time you can divide by 2, you can apply this trick. And what is this? A butterfly network. I gave a talk about that a few weeks ago when Mary and John were retiring. So that suggests it's the right thing to do, because it's a concept that already exists. So that's the reasonable guess. I try to do a butterfly network as far as I can. I divide by 2 and I can't do it in all number of inputs. I just give up and say I do that weird symmetric comparison, but then I don't go further anymore because I can't make any smart guesses anymore. So the more factors of 2 there are in my number of inputs, the larger the prefix gets and the easier the subproblem becomes, even when it's a larger number of inputs. Okay, so what happens when you do this? Where this is the 16 inputs to 2 median outputs, the smallest one. It has 51 comparators. And note that it also happens to compute the minimum and the maximum. Because that's what the butterfly already does. So when you have a full butterfly, you automatically get the minimum and the maximum, and you only have to find a network on the wires in the middle. Okay, that's great. So this recipe is this: to create a median for n inputs when n is odd, we find the median of 2 median of n minus 1 inputs. N minus 1 is even. I call this prefix of n minus 1 to 2, and then we add this little merge network that I call merge 2 because I have 2 sorted inputs and I merge them into 1 sorted output. Okay, so let me just take you through some things. Here's how to do a median for 5 inputs. I have something that for 4 inputs computes the middle 2, and then it merges it to find the final thing. But if you go from 4 inputs to the middle 2, you sort the whole thing automatically. So this is just the 4 sorter plus merge 2. This is the optimal median for 5 inputs. This is for 7 inputs. Yeah, so we go to compute from 6 inputs to 2 and then the merge 2. This is also optimal.
A question about
Yes.
optimal couldn't be that you can optimize for number of comparators or the number of layers.
Oh, very good question. Right now I'm only optimized for number of comparators, but number of layers is of course interesting if you care about other physical aspects. But for now, it's just number of comparators.
But it could be that.
Yes, and then for sorting networks, there are indeed sorting networks that are slightly more layers but less comparators, or fewer layers but a little bit more comparators, and that's depending on how you want to use them. Yes, and I guess the same is true for medians. But I only looked at number of comparators so far. Right. For an n, this is nice. So that's an 8 input merge to 2, and then you add 1. So that works nice. For 11 inputs. I didn't write it's optimal anymore because I don't know what the optimal is for median, but it's optimal for this method, meaning the subsolver terminates and says, I cannot do any better, which is a nice thing to know. If I want to have a better network, I need to have a different method. That's very good to know. For 13 inputs, works nice. And these take maybe a few seconds to a few minutes to compute all of these. And then 15 inputs, it works fine as well. 17 inputs, you get the 16 network. This is really fast. 16 is really easy to compute because the prefix is so large. So this is optimal for this method again. And then we get to 19 inputs, and then it works. We can compute the median from 18 inputs to 2 and then add a wire, but that's a hard subproblem. So I can give it more comparators and it will come up with a network And I, for a while, I thought that was the best I could do, but actually, I can do better because this sub instance doesn't terminate. So I don't know if there's any better solutions to it. So why is it hard? Because 18 is a big number. These numbers are getting bigger, but also the prefix is so small. There's only one factor of 8 in 18. Sorry, one factor of 2 in 18. I divide by 2, and then I have 2 inputs of size 9. So there's several things you can try to do, and I tried many of them. What I did was this: instead of computing the 18 to 2 prefix, I compute the 16 to 4 prefix. Why? Because 16 is so nice. I love 16, and it's such a nice prefix. But I compute 4 sorted outputs in the median instead of 2. So this is 53 comparators, 16 to 4. But now I need a merge network that adds more inputs, right? Because I only have 16 inputs and I need 19, so I need to add 3 more inputs. So how do I do that? I have this little merge network that takes in 4 sorted inputs and 2 unsorted inputs and merges them into 2 sorted inputs as a median, like that. So I can take these 4 sorted inputs, put 2 more wires in the middle, I'll put this network on it. I computed this network using the subsolver, it's the optimal network for that. And then finally I add 1 wire like I always do. So this is the optimal network that goes from 4 sorted inputs, 2 unsorted ones to 2 median ones. But also the combination of these two, I cannot do better by just saying, okay, let's find an odd input network that is not symmetrical. That doesn't do a better job than just doing an even one and finding a symmetrical one and then adding the last 2 comparators to it. That was really encouraging. So it seems to me that sticking to even number of inputs and into symmetrical networks doesn't cost anything. I have not found a single instance of any of these things I do where I can do better by searching for asymmetrical odd input networks. So that's nice. But again, I have no proof that that's the case. So here's the 16 inputs to 4 output median network. It has 53 comparators, I think, and it computes them in NMX also, but also these 4. And then the final 19 input one looks like that. So it's pretty empty here in the middle. And this comparator here actually wasn't there at the beginning. It comes all the way from here, but my print function greedily computes the layer. So yeah, maybe I should change my print function. Okay, 21 inputs again is hard. But I do it from 16 to 6. And I have this merge network that merges 6 sorted inputs with 4 unsorted inputs. And then finally I wire like that. And that's an optimal combination as well. And this is the network, 70 comparators for 21 inputs. 23 inputs, very hard. There was only one stupid method I could think. What's the stupid method? Mary, what would you do for 23 inputs?
Start with 25.
23 and 25 minus 2. So I just take the good one for 25 and I add the cut at the top and the bottom. Remove 10 comparators. So that's the best I can do. I'm not proud of it, but yeah. Okay, 25 inputs. That's the crown of the work. What happens to 25 inputs? Well, again, prefix 24 to 2 is a hard solve problem. There are 3 factors of 2 in 24, 2 times 2 times 2. But then the prefix is not large enough to make my subsolver happy. It takes a long time. It's doing that right now. So what do? I look at Paeth and I look at Mary, and they use 3 sorters. So why not use a 3 sorter? So 24 is 2 times 2 times 2 times 3. So I decompose the prefix with 2s, and finally I have 3 groups of 3 inputs left. What do I do with them? I just sort them with a 3 sorter. So that's what I do. And then the prefix 24 to 2 is not a problem anymore. Right, that's a 3 sorter I'm using, by the way. And here's the final network. You can see the butterfly-like decomposition here. There's one butterfly here, one butterfly there, one butterfly there, and then I only have groups of 3 left. Like the maximum, the maximum, the maximum of those, and the next one, the next one, the next one of those. And here's then is 8 3 sorters in parallel. So this is the first wire of the 3 sorter, this is the second wire of the 3 sorter, and this is the last wire of the 3 sorter. And it's laid out so that it's still symmetrical. So because I somehow am obsessed with symmetry. And then so that's the prefix, and then this part is just computed by the subsolver from here to there, and those are the last 2 comparators. And that takes a few hours to do, to get to 94 comparators. Okay, you can use three sorters in these other prefix ones, the 12 one and the 18 one, but for those, using a three sorter is worse than just letting it go. So that shows that using a three sorter cripples you a little bit. It's a decision you make to get scalability, but it doesn't, it may remove optimality. So I have concrete evidence that using three sorters they remove the optimal things. So 27 inputs, that's the last network I will show you. I use prefix 24 to 4, and then I use a merge 4 one. And so it looks very similar to in the middle, but it's a little bit wider here. Again, one comparator escaped from the back, and then I have a merge 4 network here somewhere, and then there's two comparators at the end. And that's 170 comparators. Neither Mary nor Paeth published the 27 inputs network, but you can take their 25 because they started with the 27 and cut the wires. So I just put the wire back again. And then Mary has a 108 comparator network. I thought for a long time that was the best. And Paeth has a 111 one. But suddenly, one day I woke up because my computer keeps trying to, and then suddenly said, hey, I found a 170 comparator, one for 27 inputs. That was a few days ago. Right. I don't know how much time I have.
You have 10 minutes.
Okay. Right, okay, so to summary, there's three things that we look at. It's the shape, where the circuit comes from, sorry, the network comes from. You have to find a reasonable prefix, and there's a subproblem. And so even on rainbows, that's a good shape. It makes everything nicer. And this prefix to 2 and then merge 2 thing, adding one more wire, seems to be a good idea. Reasonable prefix, you divide by 2 and do the comparators until it's odd, and then you just make a reasonable choice. That seems to be a good idea. The subproblem, you assume symmetry to cut the problem in half, or actually better than half. Those are the main ideas. And then some things will maybe prefix to k, and then merge k is maybe sometimes a good idea when for k not equal to 2. Maybe you can use a 3 sorter here and there instead of divide by 2 until odd. Those are sort of not, I know they're not optimal, but they lead to nice networks anyway. So, right. Yeah, these assumptions are made. I think they were all reasonable. I have not found any concrete evidence that sticking to an even number of wires hampers optimality, or sticking to symmetry hampers optimality. I have not seen that at all. Or having this prefix where you just keep dividing by 2, like a butterfly-like thing. I have not seen that makes anything not optimal. So that seems to be reasonable assumptions, but somebody will have to prove that this is actually doesn't hamper optimality, and I don't know how to prove that. Right, I have 3 separate uses of a subsolver. The first one, it enumerates the outputs of the prefix. That's one such instance. The second one finds the postfix, solves the problem. Takes most time. And then finally, when I create the network, I verify for each output what its properties are. That's also a subcall, just to be sure. Many times you make mistakes and you think you did the great thing, and then it wasn't a media network. So once you make that mistake a few times, then you build it into your pre-function so you will never make the mistake again. Okay, this slide was made by Gemini because it's about Gemini. So it said, would you like me to beautify your slide? Okay, and I said, yes, I'd like to do this slide. So there's a thing called Alpha Evolve made by Google DeepMind, and it's about algorithm discovery. Maybe you've seen it in the news. Oh, it found, for example, a faster way to do 4 times 4 complex matrix multiplication. Only 48 multiplications, primitive multiplitions instead of 49. And I read this, and it says, oh, AI is taking over the humans. And then I'm thinking, oh, so people have been using subsolvers to do these kind of things for a long time, those matrix multiplications. And they are less computationally demanding, much less. You can run them on your laptop, and you get guarantees from them. And I don't really understand the fixation with, because many of these things we know how to do with normal methods. And maybe people didn't even try it, and then they go for the news. So I would like to go for the news saying, I found a better way of doing media networks using AI, but it's really a subsolver. But that used to be called AI, so I don't know. By the way, why is there a record here? Because I used the word record, the previous record was
Artificial.
Okay, so what I'm doing right now and what I want to do, I still don't really like the 24 to 2. I think I can do better than that. So And I also want to document exactly what is optimal or not. I haven't really done that. I've just ran this for hours and then. So maybe I can improve the ones I already have, and maybe I should optimize the number of layers. That's one thing I should definitely look at. I haven't done that. And then I think, okay, if I can rule that go to 2 sources and 3 sources, why is that? Because NVIDIA GPUs, they support 3 sources. There's a one instruction that computes the maximum of 3 numbers, the middle of 3 numbers, and the smallest of 3 numbers. So that's a very cheap 3 sorter. So then it doesn't cost 3 comparators, which is 6 min-max operations. It only costs 3. So that makes sense to have them. So I should add that and compute new networks to be used on GPUs. So that would be a fun thing to do. But then you have to find a symmetry notion for 2 sources and 3 sources. And Mary and I discussed this, but the one that we came up with wasn't quite right. It hampers optimality. So other kind of networks, we're looking at both Mary and me, sorting networks, but also k-best. So you get a bunch of inputs and you want to compute the k-best ones. I'm working on a technical report, and my plan was before Christmas to send a small paper to the Signal Processing Letters, which is a journal that has a fast turnaround time, and just say, hey, I found a better network, here it is, and then refer to the technical report is my aim. But you have all these papers there, right? In this one?
No.
No. Okay.
But it should be, I mean, if it's similar to the computer architecture letters, it should be a very fast
Right.
thing.
And it's clear it's an improvement. So I don't see any problem.
It's a fast, usually it's in computer architecture letters, it's 4 pages. So it's a small paper with a very fast.
And it's better than painting in there, I think. So I'm not going to try.
That's up to you.
That's it. That's the last time. Yeah.
Yes, Powerosum 2 were good.
Yeah.
So did you try 32?
No. No, I did, and I didn't seriously try it. I just ran it for an hour or so while I was doing other things, and then I said Control C. But I should have added to my thing where I run things overnight and stuff. I should try that. Yes, I have not tried it.
Will you try matrix multiplication?
Okay, so finally, I when the alpha evolve news came out, I thought, oh, this should be done by a self-solver. So I started hacking, and then after 2 days of hacking, I started reading papers, and then there's lots of papers how to do this with self-solvers, but also they somehow cheated or bent the rules a little bit in the alpha evolve thing, so they allow more operations than what you would think, and so I don't know. So. Right. So people have used self-solver for these kind of things, but not for the specific situation that the Google DeepMind people, they bent the rules a little bit so they could shave off a multiplication. So I don't know. Yeah, and then I sort of lost interest after a while. I like hacking. I don't like reading tons of papers about something that I'm not really interested in. So, hey, Carl?
You enumerate the inputs.
Yeah.
Because that's already a counter quantification. Can you try to think about trying a quantifier? The quantifier.
You mean
QSET solver?
Oh, so no, I haven't tried that, and I also think maybe I should try it. I just assume that since I know exactly this is if you know how to do these things, there's like 1 hour quantifier. This is usually better, and there's almost no shared stuff in the middle. So I don't expect that to have any benefit, but I guess it should be tried. You can also try to use BDDs. I found a paper that used BDDs for these kind of things.
It will blow up.
Yeah, maybe. I don't know.
Sure.
Well, I mean, you think it will blow. I think the QBF solver won't do anything, but it should be tried at least.
So Patrick raised his hand in the chat.
But we can't hear it.
If you write in the chat, I can read it out.
No, I'm here. I mean, or am I not audible?
Yeah, the audio isn't working, so you're not going to hear it.
But John's going to say something.
Well,
Do you hear me now?
If he writes in the chat, I can read it out.
Okay, well, let me then.
Yeah, you've only done the optimality in a number of these particular components.
Yeah.
And I wonder if that's really the thing you would care about in practice. Don't you usually have something you want to minimize the time it takes or the power it uses? I mean, you've limited yourself to this particular component.
Yeah.
And as you say, there are 3 sorters, and if you do it in hardware, you can do many more things. You can compare many things at the same time.
Yeah, that would be much more complicated. I know that he's done that also. It would be interesting, but not at a time. I think maybe the three sorter instructions would be interesting. So the nice thing about these networks is it's so general. It works with 4 different backends.
But I mean, I could say I have the limitation. I can only have 2 layers of things. That's all you can get. You don't have to stick to 2 sorters. You can do something else.
Yeah.
Because I'm taking this particular example because the network I designed that I think computed top 3 out of 17. I have 2 clock cycles to do it. So you can't do this sort of.
Oh, you want to do top 3 out of 17? I mean, this is not. I have instances of that. Yeah, top 3 out of 17.
But many more layers.
Many more layers.
Yeah, but I only have 2 clock cycles, so you have to do it in a different way.
So but your instruction set is much richer than having min-max.
Oh yeah. You can do. You have gates.
And also you use what the data is. You know, it's floating point numbers or integers or something like that. Yes.
4-bit numbers.
Okay, 4-bit numbers. Now we're talking. Yeah. Okay. Yeah.
Ethernet priority.
Yeah. I mean, so this is very general, right? But there's a cost associated with generality. Yeah. Has Patrick written anything yet? No.
I'm not sure if my sound.
For you, if you're looking for the book, it's in the Flemish library.
Okay.
If you want to look at the physical copy.
Okay, but then I have to walk there all the way.
Yeah, again,
it's raining.
Got the appendix on.
Appendix.
Yeah, so the appendix is explicitly stated to be open source, so it should be more easily available than on an obscure Swiss FTP server.
Maybe you can ask them at the library to include appendix as well.
Yeah, maybe. But I don't know if there's. I don't know. The library doesn't do it. Does it do electronic zip files?
They do electronic stuff as well.
Great.
At the time, they had floppies or CD-ROMs attached
At
to
the
both.
back.
I think that it
Yeah.
doesn't say anything about introduction, but that's what I envisioned it would be. Yes. Although it said you find it where you find your source code. And I was like, wait,
Is it on the CD-ROM at the back?
So I have a quick question. So NVIDIA has these 2 sorters and 3 sorters, right?
but it has min-max and it has min-3 max.
Maybe the version they showed in the manual makes sense, considering that.
No, because they talked about a median of 9,
Yeah.
where they use the 3 sorter thing. And then they talk about median of 25, where they only use 2 sorters. I mean, the network they show is exactly a comparator network as this one. And they're so proud because it's really a 25 sorter, I think, and they remove lots of comparators at the end because those are not needed if you compute the median. Yeah.
But removing from only from backwards from the end is.
That's not.
Not enough.
Yeah. Yes.
So yeah, for some networks you don't know if you're optimal or not. For the smaller one, you know, but you have this nice structure, but you add some stuff afterwards.
Yes.
And your thing is okay here. I'm wondering if have you checked, is it possible to reuse those by breaking the structure and mixing your 3 sorters that you added at the end?
Right, okay, so that's a good question. So of course, I mean, I would like to break that structure, but if I do it, then the problem becomes untractable for me computationally.
Well, you get your solution, and afterwards you look. I don't know, different kind of.
Oh, if I can remove anything from the beginning,
Yeah,
anything you remove breaks the whole thing.
Yeah,
it's always super tight.
You cannot find like kind of a subset that.
No, that's
there is no reduction at all in those things. Okay.
No. So for the smaller sizes, I didn't use a prefix, and I said do all node symmetry, and it finds the optimal ones, and so you cannot do better than that. So and then with my constructor, I find the same size. So then I have a little bit more faith that I'm not paying too much from these assumptions. But yeah.
Okay, final question
From Patrick in the chat.
Yes.
So what about approximation? For example, finding a small k of elements which contain the median.
Yeah. That's the paper I mentioned that used PDDs that was published or on the upload to the archive a month ago. It solves that problem. So it's almost median. Although they have very bad results in this paper. But so again, if you do machine learning, you maybe don't care about exact median, you just care about something that's in the middle. And that may be much cheaper than computing the exact median. Yes. So, and I've not done that. It would be easy to adapt what I have to, because the correctness criterion is just a sub thing. So you could say find three things, then and the meaning should be in there somewhere. But yeah, I haven't done that.
Okay, thank you.
Very much so.